Hi, and welcome back. I want to discuss this series of 1 over n cubed from 1 to an infinity. And what is defined as the remainder, r sub n, is the summation from n equals to capital N, and this n and this n have a correspondence. Okay, so those are intentionally the same. So this series, it picks up its first term that you add or compute is going to be 1 over capital N cubed. Then the very next one is going to be from n plus 1 quantity cubed, and so on. It keeps going to infinity. This is the remainder, starting at n. Okay, and we have a way of estimating the remainder, and it relates to our integral test. It's very similar. So let me draw this. Okay, so one thing I'm going to put this summation, or let me put r sub n. I'll put both actually. So I'm going to put r sub n here, which to clarify is the summation from n equals capital N to infinity of a sub n. Okay, and I'm going to come up with two bounds for the remainder. Okay. So let me put this in color. Let me color code this. So one of them I'll do in blue. So if I look at n, okay, n plus 1, and I inscribe this rectangle. It starts at n, right? And it goes to n plus 1. We should notice, hey, I'm using right endpoints. And, if I had this n plus 3 right here, hey, that this integral, if I write out what this area is, this is going to be 1 over n plus 1 cubed, right? 1 over n plus 2 cubed, etc. 1 over n plus 3 quantity cubed. We should notice, hey, that this integral is an overestimate. So if I integrate from 1, so what this is telling me, what these right endpoints in these blue boxes are telling me, is that this integral starting at from n to infinity, okay? And by the way, I need to modify this just slightly. R sub n, the starting index, is going to be at capital N plus 1. This integral from n to infinity of f of x dx is going to have less area than the integral from n to infinity. Okay. Okay. So that's a very important correction here, just that we have this starts at n, capital N plus 1. Okay. Now let me draw the next set in blue. Okay. What I'm going to do now is I'm going to start at n plus 1 again, but I'm going to inscribe area this way. Okay. And now what we can see is that this sequence of R sub n. So here, this is going to have area of the red rectangles. This is going to be n plus 1 quantity cubed. This one is going to be 1 over n plus 2 quantity cubed, right? And this one is going to be 1 over n plus 3 quantity cubed. That the area of the red rectangles, they overestimate the integral from n plus 1 to infinity of f of x dx. And one thing that I should point out is that a sub n is equal to f sub x, okay, f sub n, okay. So this is a key relationship. And what this tells us is it gives us a remainder estimate, what we just proved in this example, okay. And we didn't prove it in full generality, but the idea is conveyed, is this remainder. So there's this theorem, and it's the remainder estimate for the integral test. Okay, and it says this. It says suppose f of k is equal to a sub k, where f of x is a continuous positive decreasing function. Okay, and we'll say that this is for x bigger than or equal to n, and that this summation of a sub n is convergent, say from n equals 1 to infinity. And then we have this set of inequalities, n plus 1, infinity, f of x dx is less than or equal to this remainder term that was defined above, and this integral that starts at n. Okay. And here's going to be my question. How good is using the first ten terms of the series? Where we sum from n equals 1 to 10 of 1 over n cubed. Okay. And, if you're wondering how good is it compared to what? Compared to taking the full infinite number of terms. Okay. Well, I'm just going to calculate what the difference would be. Okay. And I'm going to come up with some bounds. So I'm going to have this summation. Okay. I'm going to have this summation from n equals 1 to 10 of 1 over n cubed plus the summation from n equals 11 to infinity of 1 over n cubed. And you should notice, hey, if I put these two together, that's the full series, okay, of 1 over n cubed. this thing here, that's defined to be R sub 10. And I'm going to say, hey, what happens if I just calculate the first 10 terms? How good is it that if I computed all infinity of the terms? So I want an approximation, okay? Well, I'm going to have this R sub 11, right? Excuse me, R sub 10. Excuse me, one more. I had it right the first time. R sub 11 to infinity of this 1 over x cubed dx is bigger than or equal to this R sub 10. And the theorem says this is less than or equal to 10 to infinity of 1 over x cubed dx. Well, let's just calculate the maximum this could be. This would be this limit as b goes to infinity of this integral from 10 to b of 1 over x cubed dx. So will be this limit as b goes to infinity of, we already anti-differentiated this, 1 over 2 x squared, and this whole thing is negative. Then we need to evaluate at 10 and b. We're going to do this limit, b goes to infinity, of minus 1 over 2b squared plus 1 over 2 times 10 squared. Well, that limit evaluates to 0. The other term is 1 over 200. So if we compute the sum of the first 10 terms, we've approximated our answer to within 1 out of 200. Okay, and that seems pretty good. But I could also solve for how much accuracy I needed. Like maybe this is a situation where I need a lot of accuracy. I need a lot of precision. Maybe 1/1000th is the most amount of error I could have. Well, I could figure out what that would be by solving for the number of terms. Okay, and that's an application of this remainder estimate. Okay. This remainder estimate right here that I'm boxing allows us to calculate that. Okay, well, thank you very much.